Compton scattering. The third clue to the quantum nature of radiation came from the study of the Compton scattering. As we will see, the Compton scattering, like blackbody radiation and photoelectric effect, cannot be explained by classical physics. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. But before explaining Compton scattering, we must define what scattering is. Scattering is the phenomenon by which a beam of light or any radiation is redirected in many different directions when it interacts with a particle of matter. The Compton effect is the process by which X-rays are scattered from loosely bound, nearly free electrons on some materials. Arthur Compton in 1922 directed an X-ray beam toward a block of graphite and measured the wavelength of the X-rays scattered from the target. He found that the scattered X-rays had a slightly longer wavelength than the X-rays and that the change in wavelength depends on the angle through which the radiation is scattered. A schematic diagram of the device used by Compton is shown in figure below. This result cannot be explained with classical physics, because according to the classical wave picture, the electron absorbs the energy of this radiation, causing excitation of the electron, which would oscillate in response to the oscillating electric field of the wave. The oscillating electron would act like a miniature antenna, releasing the energy in a new direction as scattered waves. The scattered radiation is less energetic than the incident radiation, the difference going to the kinetic energy of the electron, but has the same wavelength. Compton interpreted the scattering process simply as an interaction, a collision in the classical sense of particles, between a single photon and an electron, in which Compton assumed that the photon behaves like a particle. The scattered photon, having lost energy, has a longer wavelength than the incident photon. The electron recoils just as if struck by a classical particle. Let's see how the photon theory combined with the principles of conservation of energy and conservation of momentum leads to an understanding of Compton's results. Consider a photon of energy E colliding elastically with an electron at rest. Initially, the photon has energy E and linear momentum P given by equations. The electron initially at rest has rest energy given by mass times c squared. After the scattering, the photon has energy A prime and momentum P prime, and it moves in a direction at an angle phi with respect to the direction of the incident photon, while the scattered electron moves making an angle theta. The conservation of momentum gives. Rearranging these equations, we get squaring both sides of each produces. Adding the results, we obtain We now turn to the law of conservation of energy. The energy of the incident photon plus the rest energy of the electron is equal to the energy of the scattered photon plus the total energy of the electron after scattering. The electron recoil energy may be in the relativistic range, so we have to use the relativistic energy-momentum relationships. Using the relationship between the energy of a photon and its momentum gives. Rearranging the terms gives. Squaring both sides of each produces. We now replace the momentum of the electron after collision into this expression. After cancelling several terms, we obtain the equation. Finally, we replace p prime with h divided by lambda prime and p with h divided by lambda. We use this equation to find the wavelength of the scattered photons. This equation is known as Compton's equation. The combination of constants is known as the Compton wavelength, and we can rewrite the equations as follows. Let's see how it works. To find the wavelength of the scattered X-ray, we use the Compton's equation. To solve item B, we need to find the fraction of energy lost by the photon in the collision. Rewrite the energy in terms of wavelength. The kinetic energy gained by the scattered electrons is the difference of energy between the initial photons and the scattered photons. The next two examples are simple. You should solve them yourself and then check the answers.